All right, take 42. Here we go again. So, as we were just mentioning there, we are talking about molarity, which again is the most common sort of unit of concentration. You should think of molarity once again as sort of a formula, really. We actually do solve for all three of these things as we talked about. Again, if you want liters, that is moles divided by molarity. If you want moles, that is liters times molarity. And a reminder that if you do have a sort of number with molarity, as we talked about, very, very good idea to really take a more dimensional analysis approach, and also really good idea to get rid of the big M. And as I mentioned, that would be 4.50 moles per liter. The number always stays with the moles part. It's always per 1 liter. And really, you should think of it kind of like dimensional analysis, a sort of conversion factor. You could use it like that. You could also, if you needed to, in a dimensional analysis sort of approach, flip it on its head there. And once again, the benefit, as we've been talking about, taking that more dimensional analysis approach, is you don't really have to worry about rearranging those equations. You can just kind of do what we normally do when we do dimensional analysis, which is opposite places cancel out the units. And it takes care of all this sort of, should I multiply, should I divide? Because when you set it up that way, again, everything on top like normal gets multiplied, everything on the bottom gets divided. So again, if you needed something like liters and you had moles, all you have to do is know, okay, I should probably use that one. Moles are on the bottom. And again, we're going to multiply and divide, and it takes care of, again, all the rearranging for you. Or if you need moles, or you want moles and you have liters, you'd use the one on the left there, and you got your moles up on top and your liters on the bottom. Again, multiply, divide. Don't have to think about rearranging the equation. All right, so we did some examples. Let's do a few more here before lecture's over. All right, so for each of these here, let's talk about the concentrations of each of the ions in each of these solutions. So these are two separate sort of problems. So for the first one, I'm looking for the concentration of the sodium ions in that solution. And for the second one, I'm looking for the concentrations of the potassium and chromate in this solution, and obviously the sulfate in the top one as well. So go ahead, take a few minutes there. I'll spit that out maybe. Take a few minutes there and figure out the concentration of the two ions present here and the two ions present here. Yeah. Okay, so let's take a look. So remember, sometimes we're not maybe interested in the whole entire ionic compound, and sometimes in solutions, because they are ionic, they will break apart into ions. We may just be interested in the ions that are floating around. So when we think about this, we want to think about how it breaks apart. So that is two sodium ions that's going to break apart into, and also one sulfate ion in this case. Now remember, as we talked about, how molarity works is there's a long way and a quick way you could get to the concentration of the ions. And really the quick way is just to kind of do almost like a stoichiometry sort of move. And we basically can look at it and go, this is a 1-to-2 relationship between that and the sodium ions. So how that affects molarity is we multiply the molarity by 2. And that will get me, without the use of a calculator, hopefully 2.4 molar is the concentration of just the sodium ions that are floating around in that particular solution. So just the sodium ions floating around would be 2.4. When we look at sulfate, it's a 1-to-1 relationship, which means basically we just multiply the molarity by 1. It really doesn't change. It's 1.2 molar of our sulfate ions. This would be our sodium as well. And again, if you just kind of look at visually what we got going on here, we got twice as much sodium ions as we do sulfate ions. And it is twice as concentrated in sodium as it is sulfate. And that's what we see when we look at the concentrations. Again, we got twice the concentration there. Same thing for our second one here. It breaks apart into two potassium ions and a chromate ion. And we could do the same thing. It is a 1-to-2 relationship here. Again, the whole thing is 0.75 molar. So here again, we would need to multiply the molarity by 2. And it's too early to do math. There we go. 1.5 molar here. potassium ions floating around in there. And again, it's a 1-to-1 relationship between those guys. So again, it's 1 times our 0.75 molar gives us 0.75 molar for our chromate ions that are present. And again, if you kind of look at what would be happening in that, we would again get really twice the amount of potassium ions floating around as we do chromate. So once again, it's twice as concentrated in terms of potassium than it is in chromate. Any questions on that? And again, this is the shorter version of really just doing stoichiometry. So again, just to show you the sodium one more time, the long version of it, 1.2 moles per liter of the whole thing here. And again, basically all we're doing is a mole to mole relationship from how it breaks apart. 1 mole of the whole thing gives us 2 moles of the sodium ions. These guys cancel, and that is why we're basically multiplying it by 2 there. That's basically what we're doing. It's kind of the long version of it, and that will get us 2.40 moles per liter of sodium ions. Yeah. Any questions on that there? All right. So let's take a look at how we could use this sort of in the problem. So we want to know how many moles of calcium and chloride ions are present in 42 milliliters of a 0.35 molar calcium chloride solution. So what we want to think about is a couple of things here. We could think about what's given to us, and we're looking for, we have molarity, which is moles per liter. And we do have the molarity of the whole thing, which is 0.35 molar calcium chloride. We also have the volume here, which is 42 milliliters. So you really could do this one of two ways. You could either do it as the whole thing together, or because we're actually just interested really in the ions, you could just get the concentration of the ions first and just kind of do the molarity calculation for them at that point. So I'm going to take that approach. So when we look at something like calcium chloride, again, it's going to break apart into a calcium ion and 2 chloride ions here. And once again, the molarity of the whole thing is 0.35 molar, which is a 1-to-1 relationship between those two guys, which means for the calcium is 0.35 molar, but it is a 1-to-2 relationship here for our chloride. So that's going to be 2 times 0.35 molar. And again, that's going to get me like a 0.7, I believe here, 0.7 molar for our chloride ions, and this is for our calcium ions. So now I actually have the molarity of each ion separately, and I could just do the molarity equation twice. So here I do need to convert, as we talked about, always when you're using molarity and volume, liters is what you need, so 0.0420 liters. And I could rearrange it and use this as a conversion factor. So if I'm looking at the calcium, that basically means I have 0.35 moles per liter of calcium. And in this case, I do have the volume, so I could take 0.0420 liters times the molarity of my calcium of 0.35 moles per liter of calcium. Liters are going to cancel, again, taking a more dimensional analysis approach here. That's going to get me 0.0147 moles of calcium floating around. We could also do it for our chloride. So once again, for our chloride, 0.7, getting rid of the big M, putting in both of the units so I could see it, moles per liter. For the chloride, again, same volume because it's in the same solution. We'll use our molarity here of our chloride, 0.7 moles per liter of our chloride. Again, the liters are going to cancel, and that's going to get me here 0.0294 moles of chloride in this case here. Again, twice as concentrated in chloride, twice the number of moles basically happening. Any questions on those calculations? Yeah. We're not looking for the molarity here, we're looking for the moles. Yeah. So you could have, if you had the moles of each of them divided by the liters, and that'll get you the molarity. So it's a very common sort of error sometimes people think about. And again, that's why I recommend not to leave it in their calculations as M, because a lot of times people, all they think about is moles and they don't think about the volume part of it. So remember, when you have big M, that is moles per liter. That's actually the concentration. And again, to help you do that, a lot of times kind of using both of those units like I did down here, you can see both of them and hopefully see what you're left with in this case. But if you did want, for example, the molarity of each of those and you were given the moles and the volume, you would do what you would say in that case. Yeah. Yep. Other questions? Now, also, like I said before, you could have just used the molarity of the whole thing and figured out the moles of the whole thing and then did a mole to mole relationship, and you would get the same answer as well. So you could have done that approach as well. Other questions on that? All right, so let's talk a little bit about dilution. Dilution is a procedure where we take really a more concentrated solution, bless you, and we add more solvent to it. So a lot of times when we're dealing with ionic compounds and solutions, we use water, but water doesn't always have to be the solvent. But a lot of times people think about just adding more water. And when we do add more water, we actually end up with a more dilute solution. So less concentrated solution, a more dilute solution. Because in a dilution, the only thing that we're adding is more solvent or water, for example, the moles of the solute before and after the dilution remain the same. So why is the molarity change when you do that? So if you just look at the molarity equation or formula, it is the moles of solute over the liters of solution. And remember that a solution is the solute plus the solvent, which means when you do a dilution, you're adding more solvent, which means in terms of molarity, the bottom part gets larger. So this gets larger on the bottom, which means the molarity ends up going down, right? Because you're dividing now by a larger number on the bottom than you started with. So that is why we see the molarity go down when we do a dilution, because essentially we're adding more solution, or volume of solution, and that, just mathematically speaking, is going to put a larger number on the bottom, going to drop the overall molarity in this case. So this is one way you could do a dilution. You could use a volumetric flask, and volumetric, as you know, means expensive. Don't break it. And usually volumetric things have one line on it, and that is the volume that you do, and usually 2 decimal places on volumetric stuff. And what you do is put a little bit of water in there, maybe put what you want to more concentrated solution in there, fill it to the line, give it a mixy, shaky, and you'll have your solution that you want there with the correct concentration when you're doing this. And again, there is really, just so you know, obviously no reaction going on. We're just actually just diluting the same solution. So there's nothing reacting really in this case. Now there is a way to calculate that. I personally like to roll with this one, which is classic, if you will. M1V1 equals M2V2. And most people roll with this equation here. And that is because molarity is really the most common unit of concentration that you could have. And M1V1 is like before the dilution. And M2V2 is after the dilution. So usually the ones are the more concentrated values, the 2s are the more diluted values, but truthfully it doesn't matter as long as you keep the numbers together. You could call them 1s or 2s, it doesn't really matter. Now, nowadays they like to teach people C1V1 equals C2V2, which is just generic for concentration. And V obviously is volume here. And that's really because you could actually use this equation for any type of concentration unit. So we talked about like percent mass to mass earlier, percent volume to volume, percent mass to volume. You technically could use this equation with those units as well. So it doesn't really matter. Most people do kind of go with this one, like I said, because most of the time your concentration is going to be molarity in most cases. So most people roll with that. But technically speaking, as long as the concentration units are the same on both sides, you could actually use any concentration unit you want. Now, Earlier, we talked about molarity and volume and the importance of liters times molarity, right? So that everything cancels out correctly. This is the one place where, if you want to, you can leave the volume in milliliters and it'll work out okay on both sides. But if you are using molarity and volume and not doing a dilution, put it to liters, because otherwise you will end up probably with the wrong unit. But you can actually do this in this case. And the reason it works is because of this. If you solve, for example, for M1, let's just say, would be M2 V2 divided by V1. And if we just look at units, if that's molarity, that's milliliters on top, milliliters on the bottom, they cancel, you have molarity, it works out okay in this case. Also, again, if you're solving for a volume like V1, you had molar M2, V2, and M1. That would be molarity, milliliters, molarity. They cancel out. You'll be left with milliliters in this case. So this is the one place where it is okay if you want to use molarity and the volume in milliliters. It will work out okay if you're using this equation. If you're not using this equation, put it to liters. You could also, if you want, put it to liters here in this equation as well. So it'll work out okay as well. Any questions on that there? All right, so let's take a look at one here, perhaps. What is the volume of 19 molar sodium hydroxide that you need to use to prepare 1 liter of 0.15 molar sodium hydroxide? So take a moment there. Think how. Okay, let's take a look. So really what we got going on here is a wonderful drawing here of a more concentrated 19 molar sodium hydroxide solution. We basically want to make a whole nother solution that has a volume of 1 liter. I'm going to also put 1,000 milliliters there as well, which is the same, and has a molarity of 0.15 molar. So the idea here is we got a couple of that information. Usually the more concentrated number is M1, so that would be our 19 molar. We don't know V1. We do know where we want to end up, which is at a concentration of 0.15 molar. And we do know our final volume that we're looking for is 1 liter, or again, 1,000 milliliters, whichever way you want to kind of do it in this case. So here we're going to use our M1 V1 equals M2 V2. We're going to solve for V1 by sending this guy to the other side. That's going to give us V1 is M2 V2 divided by M1. That is going to be 0.15 molar. I'll go with my 1 liter for now. And my 19 molar. Molarity here is going to cancel. That's going to get me some type of number, I imagine. That's going to get me a 0.00789. And these are liters, again, because I left this in liters. And just to give me a little easier number to look at, I'm going to go with 7.89 milliliters in this case. Now, that 7.89 milliliters is actually the amount of sodium hydroxide that I need to take out. So what that number represents is you would go to the more concentrated bottle, and you would just like that with an arrow, throw in 7.89 milliliters of my sodium hydroxide. So the question is, if I put my 7.89 milliliters of sodium hydroxide in there, and really I want a volume here of 1 liter or 1,000 milliliters, should I put 1,000 milliliters of water in with it? The answer is no, I shouldn't, because if I put 1,000 milliliters of water in it, my total volume would be how much? Like 1,007 milliliters, right? Which means my molarity would not be correct. So very often in dilution equations, you're oftentimes asked how much like water or solvent you need to put in there. So to figure that out, you usually would want to do your V2 minus your V1. So my V2, I'm going to do it in milliliters here. So I want to end up at 1,000 milliliters total volume. I've already put in there 7.89 milliliters. Guess I could have rounded a little bit there. That means roughly I need to put in there 992.11 milliliters of water with it. So I would drop in there 992.11 milliliters of water. At that point, I would have a total volume of 1,000 milliliters. And when I give it a mix, I would then have a solution that has that molarity. So sometimes people make a very big mistake when they're actually making solutions in real life, is they would go throw 1,000 milliliters of water in there, and that'll actually give you the incorrect molarity. So that's also a very, very common question, like I said, that dilution problems ask, which is how much water or something like that, or how much solvent you want to add. Any questions on that there? All right, you try another one here, maybe. What volume of water is needed to prepare 500 milliliters of a 0.25 molar calcium nitrate solution if you're starting with a... Okay, so let's take a look. So obviously here we got kind of same situation happening. We got a bottle here that's more concentrated at 5 molar calcium nitrate. And we want to make a more dilute solution. So again, no real reaction, just a little dilution happening here. We do want to end up with 500 milliliters of 0.25 molar calcium nitrate. So once again, most of the time, like I said, kind of the ones are usually the more concentrated, but it really doesn't matter as long as you keep the numbers that go together. Our M2 here will go 0.25 molar. Our V2 500 milliliters. So again, in this case, using our equation, our V1 is what we're solving for, so we'll divide the M1 to the other side. That's going to give us 0.25 molar, 500 milliliters, squeezing that in, and something 5 molar in this case. That's going to get us here 0.25 times 500 divided by 5, 25 milliliters. And remember, again, when we do get to 25 milliliters, this in this case is really not the answer, right? So this is not the volume of water, which is really what it's looking for. This is actually how much of this guy we need to take out, right? So that's how much we got to take out, which is 25 milliliters. Once again, our volume of our water would be our V2 minus our V1, which means we want to end up at 500 milliliters. And we already put in there 25 milliliters. 475 milliliters of water, I think, goes in with it. So again, we'll put our 475 milliliters of water. Mixing it up will give us our total volume here of 500. And at that point, you should have a concentration of 0.25 molar. Any questions on that there? Okay. So dilution, not too bad. Again, you can leave it in milliliters like I did there. Once again, you can also do liters. Your difference here would just be instead of 25, you would have 0.025 liters again instead of milliliters, which is perfectly fine as well. Any questions on that there? Okay. All right, so let's talk a little bit about stoichiometry involving solutions. The good news, like normal and what we talked about a little bit in lab as well, is it's really the same sort of steps. The real difference in most cases, I would say, is step number 2 and step number 3. So once again, we still want, as we talked about, balancing the equations. We still want to convert to moles. We still want to realize if it's a limiting reagent problem or not. We then want to do our mole to mole relationship, and we then want to take those moles to some other unit. So I would say in solution stoichiometry, the difference here is definitely in number 2 where you get your moles. So here to get our moles, using our molarity equation, moles would be liters times molarity. So that is very, very common. Probably the other common ending is one of 2 ways. You can kind of go to grams like normal and use the molar mass, but also very commonly you're going to be looking maybe for a volume of something, kind of like, or a molarity of something. So I would say in a lot of cases, you may actually solve for the molarity like we did in those titration problems or experiments, are very common as well. You may be given the molarity and maybe solve for the volume, which is another sort of popular ending, if you will. So those are your three sort of endings. And again, especially if you're doing titration problems, either volume or molarity is probably your common ending. If you're doing more of a precipitation type problem, something like grams would probably be where you would end. And obviously, you would use the molar mass like we've done before to get to grams if you did have the moles, and we'd use our molarity. So kind of like in gas stoichiometry, here in solution stoichiometry, we're going to kind of use molarity probably in two spots, and definitely in number 2 and number 4. You can, as in any stoichiometry problem, even though it's dealing with solutions, you can still have a limiting reagent problem. So you still want to look at, can I get to moles of each of my reactants? And if the answer is yes, then you do have to do that stoichiometry sort of calculation or limiting reagent calculation. If you really don't have enough information to get the moles of each reactant like we talked about, then it's just a basic stoichiometry. You could obviously avoid the limiting reagent part of the calculation. So let's take a look at one here. So we want to calculate the mass of solid sodium sulfate that must be added to 250 milliliters of a 0.25 molar solution of barium nitrate to precipitate out all of the ions in the form of barium sulfate. So let's take a look here, and we're going to start with our steps, which is we do need an equation in this case. So we have everything in words. So let's just go through that here. We want to calculate the mass of solid sodium sulfate that must be added. So we're going to take sodium sulfate, which is Na2SO4, as that is sodium with a +1 charge, sulfate with a -2 charge. That needs to be added to barium nitrate. Barium a +2 charge, nitrate a -1 charge, so we will need BaNO3 2 in this case. This is, as you hopefully should recognize it, a double displacement reaction, right? So we're going to switch partners here. We want to make sure, as we talked about previously, that we do end up with the proper formulas. So barium, which is +2, we'll end up with sulfate, which is -2, and that's going to give us our BaSO4, which is our solid in this case. The sodium will end up with the nitrate. Remember, though, that sodium is +1, nitrate is -1. So once again, the proper formula, NaNO3, no Na2NO3 right? So again, you want to make sure you get the right formulas down. Once we have the right formulas down, now we can take care of all the unbalancedness here and do a little balancing. I'm going to put a 2 there, and perhaps that's all I'm going to put. I think we might be good at that point. So just a 2 on the right gives us 2 nitrates on both sides, 2 sodiums, 1 sulfate on both sides, and also 1 barium. So I think we are good. First off, any questions on the equation here? Now that we have the equation, we want to sort of analyze what was given to us. So we definitely are given that we have 250 milliliters of this guy, and he has a molarity of 0.2 molar. And that's pretty much all we're given. So we do want to convert to moles. And we also should know that it is not a limiting reagent problem, right? Because we don't have any way to get to moles of each reactant. So this is a basic solution stoichiometry. So to convert this into moles, we do have to, because we're not doing a dilution here, right? We're just doing a basic molarity calculation. We do have to convert this volume into liters, so everything works out right. So we want to convert our 250 milliliters into liters, divided by 1,000, move the decimal place over 3 places, however you like it, I suppose. So now that we have that, again, I'm going to take a dimensional analysis approach, and I know that this is 0.2 moles per liter. Once again, I can see both of the units there, and that tells me all I have to do is go opposite. So I'm actually going to use it just like that, 0.2 moles per liter here. of our barium nitrate. Liters are going to cancel, and that's going to get me here 0.25 times 0.2, 0.05 moles of barium nitrate. So this is basically our step number 2. Instead of using the molar mass here, we're using the volume and the molarity to get us to moles. At this point, we could just continue on with what we're looking for. So what are we looking for here? We want the mass of sodium sulfate. So we actually want the relationship between these two in one calculation. So from the equation, it's a 1-to-1 relationship. So I could use that here. 1 mole from the balanced equation of barium nitrate gives me 1 mole of sodium sulfate. That is going to give me 0.05 moles of sodium sulfate. Now, if I want to know the mass of sodium sulfate, I could actually, in this case, use the molar mass here. So the molar mass of sodium sulfate is 2 times 2299 from the periodic table for the sodiums, plus 3207 for the sulfur, plus 4 times 16 for the oxygens. That's going to give me 142.1 as my molar mass here from the periodic table. And once again, we want moles to cancel, so grams are going to go up on top. 142.1 from the periodic table. Moles will cancel. And in this case, as you can see at the end here, we just use molar mass like normal. And that's going to give us that we need something like 7.10 grams of sodium sulfate. These again are our same 4 steps. Balance the equation, convert to moles. Actually down here, convert to moles. Our mole to mole relationship and our moles to some other unit. Any questions on that calculation there? We also are looking for barium sulfate. So I'll just steal a little bit up here, I think. So we also want to know in this question how much barium sulfate that we need. We would do the same steps, so no need to repeat. We actually would go all the way down here to step number 2, and we already got our moles of barium nitrate. So picking up from there, 0.05 moles of barium nitrate. We now would do our mole to mole relationship between the barium nitrate and the barium sulfate, and that also is a 1-to-1 relationship from the coefficients, our stoichiometry coefficients. So we'll do our mole to mole relationship. 1 mole of barium nitrate gives us 1 mole of our product here, which is our barium sulfate. And that's going to give us 0.05 moles of barium sulfate. By the way, that would be the theoretical yield in moles, right? Because this is a product, so that would be a yield. We want the grams of it, though. So we do have to go to the periodic table. That's way over there. Barium's how much? Buck, how much there? What does that say? I was going to go 137. It felt good, but it is right. What did you say, 137 point? Thank you very much. So you know you're getting old. Giant periodic table, can't see it. That's good. So we got barium there. We got sulfate at 3207 plus we also got 4 oxygens on that guy. So we got 233.4. So we'll do a 0.05 moles of barium sulfate. Once again, we're going to put grams on top because we want grams. That's a 233.4 grams of barium sulfate per mole. Moles are going to cancel. And that's going to get us here 11.7 grams of barium sulfate that was produced. Again, that would be our theoretical yield in grams. So again, this demonstrates a couple of things. Obviously, you could use our volume molarity to get moles. We can just do stoichiometry like normal. And as you can see, you could do it between reactants. You could do it to products. and get there. Any questions on any of those steps there? All right. All right, so let's take a look at this one here. And in this particular case, let's take a look at it together. We want to calculate the mass of white solid calcium carbonate that forms when we react these two guys together. So again, we need to start with an equation. So we're going to take our calcium nitrate. We're going to react it with our sodium carbonate. Once again, it is a double displacement reaction, so our calcium and carbonate is going to come together. Calcium plus 2, carbonate minus 2, going to get us CaCO3. That is going to be our solid. And the sodium and nitrate is going to come together. Once again, we want to make sure we put it together correctly first, and that's going to give us a +1 -1 combination there, and that's going to get us a NaNO3. Now that we have it, just like on the last one, we're going to now do our balancing. And once again, it looks like we just need a 2 there at the end to balance it. If we take a look at what we got going on, in this case, we have 25 milliliters of 0.1 molar. We have 20 milliliters of 0.15 molar. And we are looking for how many grams here of our calcium carbonate. Is this a basic stoichiometry problem or is it a limit reagent problem? It is a limit reagent problem. The reason I know that I got molarity and volume, that means I could get to moles. I have molarity and volume, I could get to moles. So again, it's a limit reagent problem. So we still do really the same steps. We got to get each of these into moles to start with. So we're going to convert our volume here, or we'll do our moles of our calcium nitrate. We do need to convert our volume into liters, so divide it by 1,000 gets you 0.025 liters. Once again, I'm going to get rid of the big M and remind you that again, that is moles per liter, so you can see both of the units there. And I'm going to multiply it in this case. So we'll go 0.1 moles per liter here. Liters are going to cancel, and that will get us our 0.025 times 0.1. 0.0025 moles of calcium nitrate. We're going to do basically the exact same calculation for our other reactant. So our moles of sodium carbonate will be 0.02 liters. Again, converting our volume into liters. Using our molarity here with both units showing moles per liter. Liters are going to cancel. Going to get us 0.02 times 0.150. And that's going to give us 0.003 moles of our sodium carbonate. So really the same thing that we did with the molar mass here, we're just going to get the moles of each of them. And just like we did before, this is really our starting amount, right, of each of these. So remember that you do have to do some type of calculation to determine which one's the limiting reagent. So you can't just take the smallest one, right? So you got to do some type of one. So I'm going to take this guy and figure out how much of the other one I need. So 0.0025 moles of calcium nitrate. Going to the equation, it's a 1-to-1 relationship between those two. And that's going to give me 1 mole of calcium nitrate gives me 1 mole of sodium carbonate. That means 0.0025 moles of sodium carbonate is needed. Again, that is the number I want to compare with how much I'm starting with. And in this case, do I have enough? I need 0.0025. I'm starting with 0.003. That means I have enough. That means we just determined, again in this case, that it is the calcium nitrate that is actually the limiting reagent. Any questions on that? So really just the same steps that we did previously. And remember, it's also really important that once you determine the limiting reagent, you finish your calculation using the limiting reagent. So make sure that you do that. So again, I'm going to steal up here. So we're going to start with our limiting reagent, which is here, 0.0025 moles of calcium nitrate. We're now going to do our mole-to-mole relationship between that and our product, which also happens to be a 1-to-1. By the way, they're not, as you know, always a 1-to-1, but just happens to get a little string of 1-to-1-ness here, so that's good. And 1 mole of our product, which is calcium carbonate there. That will give me 0.0025 moles of calcium carbonate. And here we're looking for grams. So once again, our molar mass. So calcium is 4008 plus 12.01 for the carbon and 3 times 16 there for the oxygen. That is going to give us a molar mass from the periodic table of 100.1 grams per mole of our calcium carbonate. That would get us here 0.25 grams of calcium carbonate would be produced. And again, this would be your theoretical yield in this case, right? As that is a product. Once again, the same steps of a normal stoichiometry problem, balanced equation, convert to moles. In this case, we did need to do our limiting reagent calculation and then picking up mole to mole and moles to some other unit. Any questions on this type of calculation here? Okay, so continue on with our theme of sort of solution stoichiometry in the vein of what we did with titrations is, as you know, with titrations, in an acid-base titration, it is a neutralization reaction. And remember that as we did, when you reach the equivalence point of a titration, the moles of the acid equals the moles of the base. That is basically what the equivalence point means. Remember, when we do a titration, you're basically adding a solution of unknown concentration to a solution of known concentration to figure out something like the molarity, like you did of the HCl solution, your acetic acid solution. We follow the same steps here. So let's take a look at this one here. We want to know what volume of 0.15 molar nitric acid is needed to neutralize 45 milliliters of 0.55 molar KOH. This is essentially a titration problem. Sometimes they're worded like that, neutralization. So really an acid-base problem here you could think of as a titration problem like we did in the lab last week. And in this case, it's up to you, but you know, it doesn't really matter. But in this case, you're probably adding the KOH, bless you, to the nitric acid in this case. So it is still really just a stoichiometry problem. So clearly, as we've been talking about, we do need an equation. So we will start with our equation. So this is an acid. We're going to react it with a base. And as we talked about when we talked about acid-base reactions, they are still double displacement reactions, right? So we're going to switch partners in this case. And we should always form water as a result of it and a salt, right? And the salt's really the ionic compound that we get when we put those guys together. Once again, we want to put it together properly, +1 and -1 in this particular case. And we do want to make sure it's balanced. And the good news here is I think it's balanced, actually. So I'm going to go with that. So it seems like we got 1 nitrate on each side. You got a couple of hydrogens and oxygen again. And that, so we're good. In this case, if we think about what's given to us in this problem, for the nitric acid, we have the molarity here, 0.1 molar. We're actually looking for the volume of this guy. For the potassium hydroxide, we have the molarity and we have the volume. So first off, is this a limiting reagent problem? This is not. Even though you do have molarity for the nitric acid, there's no way to get the moles from the information given to you, right? So this is still a basic stoichiometry problem. But what we want to think about for the nitric acid is molarity. So clearly we have the molarity. We're looking for the volume. So the one thing we're missing to be able to kind of do that is the moles. And that's where the stoichiometry part is going to come into play. So we want to kind of use the information for the other guy to figure out the volume here. And to do that, we'll have to get the moles. So this guy, we definitely could get moles from. And once again, because it's molarity and volume by itself, volume needs to go to liters. Again, that should be like a no-brainer. First thing you kind of do, move it to liters. So we're going to divide it by 1,000, which will give you 0.045 liters. We're going to use our molarity without the big M, and that is 0.55 moles per liter. Again, so we can see both of the units here. We're going to set it up so everything cancels out correctly, I hope. And this is of our KOH. Our liters will cancel 0.045 times 0.550. That's going to get us here 0.02475 moles of KOH. This again is not really what we want, right? Because we need the moles of nitric acid. So this is where the stoichiometry is going to come into play. We need to go from here to here, and we're going to do our stoichiometry part. And it is a one-to-one relationship. We've hit a lot of those here today. 1 mole of KOH from the equation gives us 1 mole of nitric acid. That is going to get us, I'll go down here, 0.02475 moles of nitric acid. That is now the missing piece that we need up here for our molarity. So now we have the moles of our nitric acid. We have the molarity. We could solve for the volume. I again am going to take a dimensional analysis approach because I have moles. I'm going to use that 0.15 moles per liter, or you could flip it around and go liters 0.15 moles. In this case, I actually do want to use the flip version of it. And again, the reason I'm doing it like this is, as I mentioned before, a number of times, I don't have to think about rearranging the molarity equation at this point, right? I just set it up so opposites cancel. I know everything on top gets multiplied, everything on the bottom gets divided, so I won't screw up the math part of it. And in this case, that's going to get me, you know, as long as you punch it in right, you won't screw up the math part of it, I suppose. 0.165 liters of nitric acid, and obviously 1 liter is 8,000 milliliters. That'll be something like 165 milliliters of nitric acid. So this is still our stoichiometry move. This is our balanced equation. This is our convert to moles. This is our mole to mole relationship. And this is our moles to some other unit. Again, hopefully you see a pretty good pattern here. Stoichiometry is pretty much just those 4 steps together. Did I screw it up somewhere? I see a lot of hands, yes? Oh, okay. What's up? Yeah. Yeah. You need to show the stoichiometry part of it because it won't always be one to one, and you should not use, even though you may see it somewhere, you should not use the dilution equation, and they definitely don't want you to do that here as a school. And sometimes people will actually call that dilution equation, that M1V1 equals M2V2, as like the titration equation. And it is in a certain situation. This happens to be that situation. If the mole-to-mole relationship's a one-to-one, you could use something like M1V1 equals M2V2, and you will get the right answer. But if the relationship is not a one-to-one, you'll get the wrong answer because you will not have the stoichiometry correct and or the mole-to-mole relationship. So they definitely want you to show it more as a stoichiometry problem than something like that. Is that your question, or did I? Same question. Okay, yeah. Did you have a question in the back? No. Okay. Yeah. Yeah. So again, sometimes people will say, "Hey, that dilution equation that we saw, you know, is they sometimes call it the titration equation." And again, it does work for a very narrow sort of situation, which is a one-to-one. And if you're not there, you will be off if the mole-to-mole relationship is not a one-to-one. So I would highly recommend only use this guy for dilution, not use it for a titration. The one place where you could use it for titration is sometimes you want to figure out how much volume to get to the equivalence point. You could use it for that, and that has worked well. But definitely you should try to avoid it for this for sure. Other questions? Ah. All right, so why don't you try this one here? What is the volume of 0.355 molar sodium hydroxide required to react with 125 milliliters of 0.5 molar